Hello everyone, my name is Kathan and today we'll be discussing the problem maximum subarray sums 2 from the sorting and searching problems of the CSES problem set. Let's begin. Let me read out the question for you. Given an array of n integers, a task is to find the maximum sum of values in a contiguous subarray between lengths a and b. So among all the subarrays whose length is between a to b, that is a plus 1 so on till b, you find me the maximum subarray sum. Right. So in the input, if you see, we have three integers n, a, and b. N being the size of array. So the next n will have all the integers x1, x2, so on till xn. And a and b are the minimum and the maximum subarray length. So what we have to do is we have to find out all the subarrays between the length a and b. So if you see here, a is less than equals to b, and you tell me the subarray sum which is maximum among these. Right. You find the sum of all the subarrays which have length between a and b, and you return me the maximum sum among them, right? And print one integer in the output with the maximum subarray sum, right? So we'll touch upon the constraints and example test case in a bit, but this question at the very high level is more of a extension of the maximum subarray sum problem that we already solved, right? We solved that problem using two approaches, if you remember, the prefix sum based approach and the Cadine's algorithm. So I highly recommend that you watch that video first, or you at least know both of the approaches that we discussed there before you hop into this one, right? Because we will reuse a lot of ideas that we developed there. Fine, let's go to the iPad and understand this question a bit more. Alright, let's talk about constraints first here. So n is less than equals to 2 into 10 power 5. So what does it say? If we try to implement an order of n square solution, it's going to consume nearly 10 power 10 operations. So you cannot do more than 10 power 8 operations in 1 second. So this solution is out of the picture. So then can we do n log n? Yes, definitely. N log n will be less than 10 power 8. So n log n is allowed. In similar ground, n is also allowed because n will be just nearly equal to 10 power 5 and so on. So we have to present solutions in this direction. And also we are considering subarrays whose length is in between the range a and b, right? So what is a subarray, guys? The subarray is a contiguous segment of the array, right? And this length is ab was also in a range 1 to n, right? So then that makes sense, right? So either you will have a subarray of size 1 or a subarray of size n. So we are not considering empty subarrays here. That is one important thing. So what the question asks us to do is you consider all the subarrays whose length is between a and b, and you return me the maximum subarray sum for such subarrays, right? So I guess the maximum subarray sum problem is clearly defined when we solve that maximum subarray sum 1, right? Now let's take example test case and understand this question a bit more. Let's say n is 8. That means we have a 8 size array and the values are like this: -1, -3, -2, -2, 5, 3, -5, 2 and 2, and a was 1 and b was 2. It means you consider all the subarrays whose size in this range 1 and 2. In other words, you consider all the subarrays first whose size is 1 and subarrays all the size is 2, and among all the subarrays you return with the maximum subarray sum. Fine, so let's just consider what are all the subarrays with size 1 and 2. Let me just first draw all the subarrays with size 1 in this yellow color. So these are all the subarrays with size 1, right? So these are all the subarrays with size 1. How many of them are? How many of those are there? Like there are 8 subarrays with size 1, right? And let's find out all the subarrays with size 2 then. So one of them is this, another one of them is this, another one of them is this. I'm just considering every 2 consecutive elements basically, right? And then one of them is this, one of them is this, then one of them is this, one of them is this. Now among all these subarrays, which subarray yields the maximum sum? This is what you have to return actually. So it's not clubbed, but I guess you can clearly see that if I combine this 5 and 3, this subarray yields the maximum sum, right? So we have to consider all the subarrays of size 1 and 2, and this subarray actually yields the maximum sum. So the answer will be this sum actually, 5 plus 3, 8. So what you have to output is 8. You have to output the maximum subarray sum for all the candidate subarrays, right? So how do you approach this question then? The one simple approach will be to just enumerate all the subarrays in this range. Now if you do that, like there are many ways to do it, but effectively what you'll have to do is you'll enumerate all these subarrays, right? Because one can ask you to have a equals to 1 and b equals to n. So if you have a equals to 1 and b equals to 1, this problem is same as the classical maximum subarray sum problem. So in this range, you will have to enumerate all the possible subarrays, and then you know how many subarrays are there. There are order of n square subarrays. So the brute force will take order of n square. So we cannot do brute force, right? So if we cannot do brute force, then what next? So if we cannot do brute force, then what do we try to think is can I find maximum subarray sum? Can I find maximum subarray sum ending at a given I, which belongs to 1 to n in optimal time, right? So this is a recurring theme in subarray based question. Can I solve this problem in a optimal time, right? Can I find the maximum subarray sum ending at I for all I belongs to 1 to n, and this like, of course, it is assumed that the subarrays are valid in the sense where subarray sizes belong to range A and B, right? So can I find a maximum subarray sum ending at a given index where the subarray size range from A to B, right? So consider all the subarrays ending at a given index and the size in range A to B. Can I do that? Now if you recall that maximum subarray sum problem, how did we calculate this MSSS of I, right? So effectively this is what we are after. So what did we do? So we use prefix sums, right? You recall the prefix sum based approach. From prefix sum of I, what did I subtract? From prefix sum of I, I subtracted minimum of 0, P1, P2, so on till Pa minus 1, right? So what did I do? From this guy, either you don't subtract anything, right? Or you subtract P1, or you subtract P2, or you subtract P3, or anything from Pa minus 1. You can subtract any one of these to actually consider all the subarrays ending at this index. But to get the subarray sum which yields maximum sum, you subtract the one which is smallest. If you subtract the prefix sum, like among all the prefix sum who has come before it, the minimum of them, then you get the maximum subarray sum ending at index I. So this we already know. Now can you can say take help from this. You can say draw parallels from this idea to this question. Now you agree with me one thing here, that if A is 1 and B is n, this problem is exactly same, right? So contribution of ith term will be Pi minus minimum of all the prefix sums before it. I take some liberty here and call this 0 as P0 only, right? So I know there are no elements at 0, but let's just call the prefix sum ending at 0th index as 0, and let me call it P0. It just simplifies a lot of things going forward. Okay, so we know that if A is 1 and B is n, then our problem is same as the maximum subarray sum. But for now, let's just say A is 1 and B is 1. So if you are at the ith index, the only subarray possible is this, right? So the only prefix sum you can say that gives your candidate subarrays Pi minus 1, right? The only candidate prefix sum. So like you were having earlier all the prefix sums, right? Your candidates were all the prefix sums before it. But if A is 1 and B is 1, then it means you only consider subarrays of size 1. In other words, when you are at ith index, the only prefix sum that you can subtract is Pi minus 1, right? So in this case, your answer will be Pi minus 1, or more concretely, Pi minus minimum of, you only had 1, Pi minus 1. Okay, let's take it a step further. Let's say you have A equals to 1 and B equals to 2. That means you are considering all the subarrays of size 1 as well as 2. So in other words, if you are at the ith index, now you can subtract this guy, or you can subtract this guy. In other words, you can either subtract Pi minus 1, or you can subtract Pi minus 2. So now your answer will be what? Pi minus minimum of Pi minus 1, Pi minus 2, right? In the same ground, if you had, let's say, some a equals to n and b equals to some k, where k is of course less than equals to n, your contribution of ith index will be pi minus minimum of pi minus 1, pi minus 2, so on, pi minus k, right? Because here you could subtract only pi minus 1 and pi minus 2 when a was 1 and b equals to 2, right? Now if I generalize it, let's say I call it like a equals to 2. If I call it a equals to 2, then pi minus 1 is not your option, right? So what I'm saying is, guys, if you have, let's say, ith index like this, and if I say the minimum subarray that you consider is of size 2, then you cannot have this pi minus 1 as one of your candidate prefix sums, right? Because if you subtract this, then it's gonna return you a subarray of size 1. But then you will start from I minus 2, right? And let's say b was 3. So we're considering all the subarrays of size 2 and 3. So that means you can subtract pi minus 2 because it's gonna give you a subarray sum of size 2. You can also subtract I minus 3, because when you subtract I minus 3, it's gonna return you subarray of size 3 as well, right? In other words, what you have to effectively do is, given any a and b, when you are at the ith index, the contribution of ith sum, or you can say the maximum subarray sum ending at ith index, and the subarray size is in range a to b, is pi minus 1 minimum of, what are all the candidate prefix sums? The first prefix sum is this, which is at I minus a, pi minus a, so on till I minus b. So minimum of pi minus a, pi minus a minus 1, so on pi minus b, right? Like, of course, technically this is representing the prefix sum here, right? So when you subtract pi minus b, you are effectively getting a subarray of size b. When you subtract pi minus a, you are effectively getting a subarray of size a, right? To get the contribution of ith term, what you have to do is, that is, what do you mean by contribution, guys? The maximum subarray sum ending at ith index and the subarray sizes are in range a to b. From pi, you subtract minimum of these, right? Because all of these prefix sums effectively correspond to one of the subarrays in range, one of the subarrays in sizes a to b, right? So that's interesting. So, and what happens is, when you move ahead, for example, when you move I to I plus 1, when you come here, now this sort of a window of prefix sums also moves ahead, right? So next time all the prefix sums that you consider will be this, right? So in other words, what you have to effectively do is, we have to make you can say track a window of prefix sums, right? And that prefix sums go from pi minus a to pi minus b. And when we slide, so in other words, when I moves ahead, when I becomes I plus plus, then this also shifts ahead, or like, if I want to show more concretely, if this was I minus b and this was I minus a, when I moves ahead, we also move ahead one step here, we also move ahead one step here. So this is gone, right? In a way, we remove one prefix sum from the left part and we add one more prefix sum from the right end, right? So it's sort of we have to slide the window while keeping track of prefix sums. So how can we do this then? So what do we have to effectively do here? If you see, we need a data structure which helps us to store the prefix sums, right? These prefix sums actually represent one of the subarrays in size a to b, okay? And not just store, we also want to you can say efficiently find the minimum of them, right? So storing is one thing. We want to store this prefix sums, and we also want to efficiently find the minimum of them. So which data structure comes to your mind? If you want to efficiently find the minimum of them, you can clearly see, if you can store them in some sorted fashion, then it would be great, right? And storing, so we want the insertion of prefix sum, right? So when we slide the window, when we slide the window, we want the insertions to be efficient as well. So this gives you idea. Then yeah, maybe we can use a multiset. Multiset because prefix sums can repeat, right? We want to store the prefix sums efficiently, and we want to efficiently find the minimum of them, right? So when we slide the window, the insertions and arrays have to be happening efficiently, right? So this gives you idea that we can store all of them in a multiset, right? Now you can do this. You can store all of them in a multiset, or there is one more way. I don't know your knowledge about this DQ, right? So what is this DQ is like? It helps us do efficient insertion and deletion at either ends, right? And effectively, if you see what we're trying to do here is, we want to remove one guy from the end and insert one guy from the start. So we want to efficiently, you can say, perform insertion deletion at the edges. So if you want to do efficient insertion deletion at the edges and also find the minimum of them, you can actually use this DQ, right? Now, and this may not be directly clear, like how will you get the minimum efficient manner, because it relies on the idea of this concept of sliding window minimum, which I'll touch upon afterwards. But I guess the map approach is pretty straightforward, right? You can store all of them in a map, and by default they'll be sorted, so you can just use begin to fetch the minimum of all the prefix sums, and when you slide it, you can remove one from the end and insert one toward the start, right? So yeah, let's look at the multi-set based approach first, because both of them are optimal approaches. Now let's first discuss the multi-set based approach using the pseudocode and sort of a high level try run. Now first things first, we need a multi-set to keep track of all the valid prefix sums. So let me call this multi-set window. Why window? Because we are gonna at a time store all the prefix sums which correspond to pi minus a to pi minus p. That is, each of the prefix sum correspond to one of the subarrays whose size is in range a to b. Then we also need to keep track of all the prefix sums. So a prefix sums array is also needed, right? So you can call it array, vector, list, or whatever you are storing it in your programming language. Let's call it p sums vector. Okay. And firstly, we know that this p sum of 0 is 0, right? So p0 is 0. So we are talking about one based indexing. So p0 of 0 means that this will actually represent the subarray of size I, right? So if you have, let's say, I equals to 2, and if you don't subtract anything, this p0 corresponds to that, right? So we already have that cleared up. Now what we will do is we'll go through every possible index and find its contribution. What is the contribution? I'll try to find the maximum subarray sum ending at every possible index, and the subarray size is in range a to b. So for that, I'll also have to initialize my answer. Since I want the maximum subarray sum, what I'll do is I'll initialize the answer to a very small value. Let's call it minus 1e18 or minus 10 power 18. Now we want to fetch the contribution from every possible index, right? And we'll try to update the answer, right? So effectively what we'll do is we'll try to update our answer like this. Answer equals to max of whatever maximum subarray sum ending at this index is an answer, right? So what are you going to do then? See, one thing is clear. Let's say A was 3 and B was 5. So if you are at index, let's say 1 and 2, if you are at index 1 and 2, there are no subarrays of size greater than, you can say, greater than equals to 3, right? So we are after the subarrays whose size is greater than equals to 3 and less than equals to 5. So if you are at index 1 and 2, no subarrays are valid at these indices, right? So there are no contributions from these indices. Or in other words, if I is less than a, if I is less than a, then continue, right? Continue. There is no need, there is no contribution from this, so the answer should not be updated for this index. But yeah, any which way, you need to calculate the prefix sum of I, right? So this is not needed, right? Basically there will be no contribution from this indices, but this p sum of 1 and 2 are required, right, for a few further processing. So we will calculate p sum of I, which will be nothing but p sum of I minus 1 plus whatever the array of I value is right now. Notice that this will always work because we already have a p sum of 0 set to 0. Okay, fine. So one thing is clear. If I is less than a, then this I is, you can say, have no contribution. There are no valid subarrays ending at these indices. But yeah, there will definitely be a subarray which ends at index 3, right? And the size will be what? 3. So there is one subarray here. So there is one subarray here which ends at index 3 and is valid. That is, the size is greater than equals to 3 and less than equals to 5. Okay. So in this case we continue. But what if I is greater than equals to a? So that means you'll be here. You'll be here when I is greater than equals to a. Okay. In that case, firstly what you will do is, so notice we always maintain a window, right? So when we move ahead, we try to expand the window, right? We try to expand the window. So when I goes from 2 to 3, I know that there will be a candidate, right? So in a way, there will be a candidate. So now you can actually subtract P0, right? You can subtract P0, that is, you can subtract nothing to get a valid subarray, right? So right now you can say the window size is 0. And as soon as I moves ahead, you try to expand the window. Try to expand the window, that is, you try to include P of 0, right? So what I'll do is, we'll do window.insert P sum of I minus a. Because if you remember, what we effectively want to do is, we will take the minimum of all the prefix sums. We'll take the minimum of all the prefix sums in a range I minus a to I minus b. So whenever I moves ahead, what you effectively do is, you first add I minus a and then you remove something before I minus b, right? I'll repeat myself again. Let's say you are moving I ahead. That means you are at this I. Now the window earlier was somewhere here. Let's just assume. Now when I is here, what you'll do is you'll try to expand this window. That is, you'll try to include I minus a. I'll try to include I minus a. And what I'll do, since this window moves ahead, I'll try to remove something. Which is less than I minus b. So this is I minus b, right? So we'll try to remove this. So the next check would be, you first check if I is greater than b. That is, for now, let's say it was 4, 5, 6. So let's say I is right now 6. Okay. So if I is 6, then firstly you're gonna add the contribution of I minus a. That is 6 minus 3, 3. You're gonna add this guy's contribution into the window, but you're also gonna remove P0, which is less than 6 minus 5, 1, right? So this is I minus b, this is I minus a. So you just added I minus a. Now you have to remove the contribution of P0, right? Because now you cannot no longer subtract P0, because if we subtract P0, it's gonna yield a subarray whose size is 6, which is greater than 5. So if I is greater than b, we are going to remove the contribution of one element just before I minus b. So if I is greater than b, from the window you erase P sum of I minus b minus 1, right? You remove the contribution of one element just before I minus b. In a way, you just slided the window. You expanded from one end and shrinked it from the other end. And after that, it's very easy. Now you already have a window which contains all the valid prefix sums. So MSSS of I will be what? It will be simply P sum of I minus begin. Right? So begin is going to return the smallest possible prefix sum. Begin of window. Right? So then you'll calculate MSSS of I and then you'll update your answer. And after the loop ends, you can just print the answer. Right, so I guess that was the approach. Now let's quickly discuss the time complexity. Right, so if you see what is happening here, we are creating here multi-set prefix sums and fine. So you can maybe pre-calculate the prefix sums, or we are calculating here on the fly. This is one the same thing. But all in all, we are going through all the indices, right? We want to calculate the contribution of every possible index, is order of n. And then, and at each operation, what we effectively do is, we either expand the window, right? Or we expand the window and shrink the window. So initially, what we effectively do is we expand the window till we have, you can say, at least till we have all the prefix sums corresponding to the subarray sizes a to b, right? And afterwards, we expand, shrink, expand, shrink, expand, shrink, right? That's what we do. So first, we are like, in a way, we have to either do insert, erase, right? So all in all, these map operations are what? Log n. Right, so order of n loop, and each time you are not doing more than some constant factor of log n. Right, so begin is a constant m operation. Right, so that's the approach. You just maintain a window of prefix sums and keep on sliding the window as you move ahead while contributing the answer from every possible index, and then update the answer at every possible index. And yeah, I hope you understood the approach. If you did, please comment understood in the comment section of the video. And let's move on to the code and solidify our understanding of this approach. Alright, so here's the multi-set based approach code. So the input, the first line we have n, a and b. So n is the size of array and a and b are, you can say, which defines the valid subarray sizes, among which we have to find the maximum subarray sum. Then notice I'm taking the array input here. Everywhere I'll use long. For reason that we are calculating sums, and since all the values are in range 10 power 9, it very well might happen that if you had to sum all of them, and all of them are positive, let's say 10 power 9, and the array size is 10 power 5, it might give you a value, the sum value which is 10 power 14, and which is higher than integer range, right? Integer range is minus 10 power 9 to plus 10 power 9, so it can cause overflow. Or if all the values are negative, then it might cause an underflow, right? Minus 10 power 14. So that's why we are taking everything as long, whose range is very high, somewhere along minus 10 power 18 to plus 10 power 18. Okay, then this is our window, which is a multi-set. Then I have prefix sums array. Notice it is of size n plus 1, right? Because we are also going to store p sum of 0. So like I'm initializing every one of them to 0, so it automatically says that p sum of 0 will be 0. Initialize my answer to a very small value because we want maximum subarray sum. Then I'll go from I to n and start collecting contributions from every possible index. First calculate p sum of I. Now, if there are no valid subarrays whose size is greater than equals to a ending at this index, then we simply continue. There is no contribution from this index, we just saw, right? Otherwise, expand the window. So whenever I'm a current I, add I minus 8th guy to the window. Also, subtract the guy 1 before I minus b, right? So if I is greater than b, you subtract p sum of I minus b minus 1, right? So now effectively what we have is we have a window of prefix sums corresponding to the sizes in range a to b. So find the contribution of I. What is contribution of I? It's p sum of I minus smallest among all the prefix sums, right? And then update the answer. And notice, like whenever you are at I, this p sum of I minus a and p sum of I minus b minus 1 always exist, right? Because this will be smaller than I, and we are already calculating p sum of I as soon as we enter the loop. That's one thing. So yeah, I guess we have already discussed. So this is order of n loop, and in that we only do some constant number of log n operations. Specifically, this insert, this find, and this erase. These are all log n based operations, right? So the time complexity is n log n, and space complexity is what? Order of n, because we are maintaining a window of all the prefix sums, right? So here we have to maintain a window of prefix sums. So in the worst case, when a is 1 and b is n, we'll have to store all the prefix sums. So in that case, the space complexity will be order of n. So yeah, I mean that is about the multi-set based approach. Now let's quickly, you can say, go through the sliding window based approach as well. Alright, let's try to look at an even more optimal approach to this problem, right? So we solved this problem in order of n log n, and turns out we can actually solve this in order of n time as well, right? And I guess one thing you already noticed, we have to first find the prefix sum and then erase it, right? Because if we directly erase it, then it's going to erase all the occurrence of that prefix sum, but we don't want to do that. Anyway, so what is the sliding window based approach? Now this CSES problem set, if you see the sliding window section of it, has the question titled as a sliding window minimum, right? So this question will use the concept used in this question. So we'll defer a detailed discussion of this question when we discuss that problem. But for now, what this problem tries to tell us is, let's understand it at a very high level and use the ideas of this question specifically for maximum subarray sum 2. Okay. So what does this sliding window minimum question ask is, you are given an array, then you are given a window, let's say some k is equal to 2. So if k equals to 2, what does it say is, if you have an array like this, let's say 1, 2, 3, 4, 5, 6, you tell me the minimum of every possible window of size 2. That's what you want to output, right? Sliding window minimum says you go through, you can say, all the windows of size k. So there will be a window size given to you, k, right? If you notice here in this question also, we have a window size defined, right? So window size is what? We consider all the prefix sums in a range, like you can say all the prefix sums that correspond to the subarrays of size in range a to b. In other words, we have all in all a window of size b minus a plus 1, right? Okay, so this question says you go through all the possible windows of size 2. So one window is this, you output its minimum, so you output 1 here. So another window is this. Your output is minimum. You output 2 here. Another window is this. So you output 3 here. Another window is this. So you output 4 here. Another window is this. You output 5 here. So all in all, if you have n and k given, there will be n minus k plus 1 windows. For n minus k plus 1 windows, you return me its minimum. You can clearly see we can use this idea, right? Because here, like in this question also, we are doing effectively same thing. We are maintaining a window where k is equal to b minus a plus 1, and the window is sliding one by one, right? And the beauty about this approach is that we are going to use it solves this problem in order of n time. And how does it do it? It uses something called as a DQ. Okay, so what is a DQ? Let me tell you what is a DQ first. So DQ is like a normal queue only. So let's just call this part front of the DQ and this part back of the DQ. Right, now the way DQ works is, so DQ, right, it allows you to do efficient insertions and deletion on either ends. That is, if it will allow you to insert or delete elements from the front in constant time, it will allow you to insert or delete element from the back in constant time. So insert, delete, or fetch. Right, so this is a very important data structure. And turns out if we use DQ for this problem, we can solve this problem in an order of n time. So the way it works is, whenever I am calculating the answer for given I, for example, whenever I'm at like the case 4 here, and I'm trying to find the minimum, you can say sliding window minimum, where you can say this window ends at I equals to 4, my DQ's front will contain the minimum, which is 1. Right, so how does it work? Let's see. So we will have a DQ here, right? So notice the DQ is here. Okay, let's do a dry run of this sliding window based approach. You will get it. Now, what we will do is we'll start processing the elements from start till the end, right? And whenever you can say the window size has become 4, you will start spitting the minimum of that window. All right. So when you are here, the window size is not yet 4, right? But you are still gonna put this guy into the DQ. So let's just put 2 here. Okay, when you are at 2, the window size is not yet 4, so you don't have to print, you can say, the minimum element now. But notice one thing. Yeah, I have to push this one into the queue. In the front, you will always have the minimum element stored, right? So if I have 1, does it make sense to have 2? It doesn't, right? So what you do is, when you try to insert an element in the DQ, you remove. So during insertion, what you do is you remove all elements greater than current, right? All greater than current from the back, right? So effectively, what you'll try to do is you'll try to insert from the back, but if there are elements greater than the current guy, you remove them. Why? Because if 1 is there, there is no need to put 2. Right, there is no need to have 2 because if there is a minimum needed, this 2 will not be the answer. So we remove this 2 and add 1 here. Okay, then we move ahead. Now when you are at 4, what you will do is you will remove any elements which are greater than 4. So if there was some 5 here, 6 here, 7 here, you remove all of them, right? Because if there is 4 and there are 5, 6, 7 before it, it doesn't make sense to have them because 4 will always be the minimum for all the windows ahead of it. Okay, but you don't remove 1 right now, right? So you only remove the elements greater than it. Then we push 4. Okay, then we move ahead. When you're here, you remove all the elements greater than this guy. There are no elements greater than this guy, so we happily just add this guy. But notice, when we are at 4, our answer has to be printed because now the window size has become 4. So here, you will output the front of DQ. So the answer, let me write the answer where? Let me write the answer above, okay? So the first window's answer is 1. So this window's answer is 1. Okay, then we move ahead. So when you move ahead, notice the window till now is of size 4. So when we move ahead, when we want to calculate the window ending at index 5, this window has to slide, right? So right now we have this window, and when we move ahead, this window has to slide, right? So now we have this window. Now, when you slide the window, you first check, is 2 present at the front, right? If 2 is present at the front, that we have to remove it, but it's not. Then we'll try to accommodate 3. Now, what do we do when we try to insert? we remove all the element greater than the current guy from the pack. And why do we do this, guys? See, if 3 is present and 4, 5 are occurring before it, for all the windows which are ahead, 3 is going to dominate this 4 and 5 because 3 is less than 4 and 5. So if there is a sliding window minimum required ahead of it, 3 is always going to dominate this 4 and 5. So this 4 and 5 should not exist in your DQ, which is representing your window, right? So then we remove 4, 5 and add 3. This is, I guess, similar to that monotonic stack question, if you can remember. Okay, so now what is the answer for I equals to 5? That is the window which ends at 5. What is the front of the queue? 1. The front of the queue is 1. So the sliding window minimum, the window's minimum, the window which ends at 5 is 1. Okay, then we move ahead. So when I is at 6, the window will slide now, right? Window will slide means you add 4 and then 1 gets removed from the window. So whenever you slide and the DQ's front is actually equal to the left bound, right? The left bound, right? The one which I just shrinked the window from, then we have to do DQ dot pop front, right? So you have to remove this 1, right? But notice, when you remove 1, automatically we have next smallest element of this window stored, right? When you remove this 1, automatically we have the next smallest of this window, right? Then we add 4, but since there are no elements greater than 4, we add 4 automatically, right? So what is the minimum here, guys? What is the minimum for this window? So this was the window, by the way, 4 size window. So what is the minimum here? 3. DQ's front. So we output 3, right? The window of size 4 ending at index 6 has a minimum of 3. Fine, let's move ahead. So when we move ahead, the window slides. So now the window is like this. So then what do? You first check, have you you can say put the minimum element out of the window. So is 4 the minimum element right now? No. So you can say the DQ dot front is not equal to the element which was just swapped out of the window. So yeah, there's nothing to be done, but when you try to insert it, you remove all the elements greater than it. This 1 dominates this 3 and 4. All the windows ahead of it is going to be dominated by this 1. So you remove this 3 and 4 and insert 1 again into the queue. Now, what is the minimum? It will be DQ's front, right? For the window of size 4 which ends at 7th index, its minimum is 4, right? So 5, 3, 4, 1, it's definitely, you can see 1 is the answer. Then we move ahead. So when you move ahead, you swap out 5, but 5 was not present in the queue, so nothing has to be done. And then you remove all the elements greater than 2 from the DQ which are not. Then we add 2 to it. And what is the minimum of this window, guys? The front of the queue, right? So front of the queue. So this will be outputted 1. So notice what just happened. We just moved from left to right of the array ones, and all we did were we efficiently, you can say, we either performed insertion, you can say deletion from the front, insertion deletion from the front, or insertion deletion from the back at most once. For every index, we performed at most 1 insertion or deletion from the front, at most 1 insertion or deletion from the back. And these are constant time operations. So all in all, the total time complexity here is just order of n. Space complexity, yeah, it can very well be order of n when you have all the elements stored in increasing order, right? So in this case, the space complexity can be order of n because you may have to store all the elements in the DQ. But yeah, that's one thing. So yeah, I mean, this is the sliding window minimum question at a very brief. Now let's see how we can reuse this idea in the code directly. All right, now let's try to reuse the idea of sliding window minimum to actually now maintain a window of all the prefix sums and to get the, you can say, minimum prefix sum for every window whose size is in range A to B. And we can do that. Let's see. So we already seen the approach using multiset. So here I've already taken the input as discussed earlier. Now let's see how we are going to solve using the DQ. Right. So firstly, I initialize my window, which is now a DQ. Right, DQ or deck, you can call it anyway. Some people call it DQ, some people call it deck, whatever you want to call it. Then I maintain a vector of prefix sums. right? Here it's also size n plus 1. So p sum of 0 is 0. Everything is same. I initialize my answer to a very small value because I am after maximum Subarray sum. Then I go from start till the end. I want to find the contribution of every possible index. That is, I want to find the maximum Subarray sum ending at every possible index and then update my answer with it. And in the end, I can just return the final answer. Now notice what we do. First, we update the p sum of I, which is simple. We are just calculating the prefix sum on the fly. That's one thing. Now, this part is also same. If I is less than a, that is there are no valid subarrays whose size is greater than equals to a ending at current index, we skip it very happily. Otherwise, what do we do, guys? If you remember the multi-set based question, when we slide the window ahead, we try to include p sum of I minus a into my window. But here the insertion logic will be used exactly similar to the sliding window minimum. So we want to include this p sum of I minus a. But before that, you remove all the elements in the window which are greater than this, because this guy is going to dominate all the elements which are greater than it, right? So while the window is not empty and the window dot back is greater than the current p sum of I minus a, so you are trying to include this element in the, you can say, window. So first remove all the elements which this guy dominates, right? So window dot pop back. Notice pop back, we are removing elements from the back, and then push back p sum of I minus a, right? And when you're sliding the window, you have to check if the element which was just swapped out was the DQ front. So if I is greater than B, you first check if the window dot front, that is the minimum element, is actually equal to the element that was swapped out. If it is the case, window dot pop front, very important, window dot pop front, remove the element from the start. And after these two end, we automatically have a window. Of prefix sums whose like we represent the size Subarray sizes from A to B. And since this is a sliding window based approach, we know for the fact that window dot front will have the smallest possible prefix sum. So to get the MSS of I from p sum of I, we can just subtract window dot front, which will automatically hold the smallest possible prefix sum of that window. Fine. And then we can update our answer. And after this loop ends, we would have taken the contribution from every possible index, and then we can return the answer. And this answer will be printed here. At time complexity, we already discussed order of n, because you can see here, this is the order of n loop, and here what are we doing? This empty check, back check, pop back check, these all are, you can say pop back, these all are constant time operations, right? There is a while loop here, but what we effectively do, we remove, if we remove or insert an element, we remove and insert an element at the back exactly once, right? This while loop is there, but all in all, you can say if we average over, the amortized time complexity here turns out to be, for this pop back won't be called more than order of n time, right? So these are, you can say, this pop back won't be called more than order of n time. This pop front won't be called more than order of n time, and this window dot front won't be called more than order of n time, right? So all in all, total time complexity turns out to be order of n, right? So yeah, I mean that's about the sliding window based approach, and this is, you can say, the most optimal approach for this solution. So I hope you got something out of this video. So we discussed in detail all the optimal approaches, and if you find this video helpful, please give it a thumbs up, and I'll see you in the next one.